Yeah, yeah. Yeah.
But does it always happen that there are both particles, gamma primes, do exist on both sides?
Yeah.
It can happen that they disappear and there is just one particle after the wall.
No, just the kinematics of this won't allow that. I don't think so. I mean, again, let's look at the process. How can I say it? So, you know, this decay is always at least a two-body decay. Now, you might ask, could it happen that the particle decays into two guys of the same charge, actually? In other words, like, you could imagine that you have a guy of just charge 2 gamma, it decays into 2 guys of charge gamma. In that case, there would be only one state on the other side, namely the state of charge gamma. It turns out that that doesn't happen. That'll be a consequence of what I'll tell you in a minute. Yeah. OK. So far, I haven't done anything. So far, I've just drawn you a picture. The picture doesn't tell you alone what the wall crossing is. But now, you do the following thing. So now you do the following thing. You consider any closed loop you like, in this kind of joint parameter space. So let me draw a picture of what this closed loop possibly could look like. It could be like, well, could be, for example, this loop. Or it could be a loop that goes around one of these places. So you consider any closed loop like this, and then Kontsevich and Soibelman say you should do the following bizarre-looking thing. You should define something attached to this loop. What will it be? Well, it'll be, I take my loop and I look at all the places where it intersects my green picture. So every time that my loop runs into a BPS state, I'm going to have a factor in this product. And what will the factor be? The factor will be this transformation of variables that I called k gamma, raised to the power omega of gamma, the BPS degeneracy, the BPS count, where the sign depends on which way we cross. Okay, this looks fierce, but I'll show you an example in a second. Yeah, so what the heck is this? So let's see what it is in these two examples. So for example, in this first picture, I'm just redrawing part of the picture that I had above. So I've got 3 charges, gamma, gamma prime, and gamma double prime. So three BPS particles. And I take this path that just does this. So in this case, Kontsevich-Soibelman's A of P is the following thing. It's just a composition of these things that we called K gamma. So I'm going around this loop, and I meet these 6 things: gamma double prime, and gamma. 1, 2, 3, and then 3 going back the other way. So when I go back the other way, I put inverses. So this says K gamma was this automorphism of the algebra. Let me just write it here again. K gamma was a thing that maps x gamma prime. Whoa. I won't say anything while I write. OK, this is just so you have in your mind, this is an absolutely concrete formula. And we're supposed to take a composition of these 6 changes of variable. OK, fine. Kontsevich-Soibelman tell you to do that. You can do that. And then on the other side, in the more interesting case that I drew here, where we have gamma, gamma prime, and a bunch of stuff. And potentially now a whole bunch of bound states of gamma and gamma prime. In this case, what their formula says you should do is you should consider, well, so once again, so here I'll just have k gamma prime k gamma for going up this leg. And then for going down the other leg, I'll have this enormous pile of stuff. So k gamma prime inverse times then a product over all the bound states that appeared, whatever they were. So they have charges m gamma plus n gamma prime. And then finally, I'll have k gamma inverse. Okay. So all right, so I can consider this thing. So on the right, I have this product which contains all of the BPS degeneracies. Here, this capital omega is counting all of these different BPS states. So this thing is some kind of complicated gadget which contains in it the information of all the BPS states. Okay, fine. That's still not a formula. That's just a definition of something. So now, finally, I can tell you what is the Kontsevich-Soibelman formula. What it says is that this gadget A at P that we defined, which a priori you get by some very complicated composition of all of these k gamma operators, that actually this A of P is just the identity for any contractible path P. So when you look at this, of course, on the right side, it's actually obvious, right? I wrote A of P in a way where I have k and k inverse, k gamma prime and k gamma prime inverse, k gamma double prime and k gamma double prime inverse, and so they just cancel each other. So it's actually obvious right away that this would be just the identity. What's much more non-trivial is that when you're going around one of these walls, that this thing should still be the identity. And so let me show you a couple examples of what that means sort of concretely. So in the picture that I called 2 above, what does it say? It says that saying that this thing is the identity is the same as saying that k gamma prime k gamma equals this product of k m gamma plus n gamma prime to the omega of m gamma plus n gamma prime. And this formula, it actually determines all the omega of gamma that appear on the right-hand side. So in this sense, it's a wall-crossing formula. It reduces the problem of understanding how the BPS spectrum changes to this completely algebraic game. You just have to solve this equation. And so let me show you a couple examples of this. So it reduces this wall crossing to a sort of purely algebraic exercise.
In the right formula, you have written that are you missing a k gamma first?
In which formula?
In the left hand, no, in the right hand side.
On the right side of this last formula?
Yes.
Oh, I see. Sorry. Yeah, you're right. So here I should have included them explicitly separately. So that's right. K gamma prime. Yeah, and then m and n here are both greater than 0. And here also m and n are both greater than 0. Right. And the order in these products matters. So when I write m over n with that down arrow, I mean it's the product in the order of decreasing value of m over n. Because these automorphisms, these transformations don't commute with each other. So you have to keep track of the order. So okay, so let's see an example of how this game works. So for example, so suppose we have two particles whose ds-z inner product is just equal to 1. That's kind of the simplest thing you can imagine. So then, here's a little algebraic identity. So the general formula that I wrote above says I should write k gamma prime k gamma. That represents just having two BPS particles on one side of a wall. And then on the other side, I'll get a huge product that tells me what are all the BPS particles that appear on the other side of the wall. Well, in this case, as it turns out, the product is actually very simple. There's just a little 3-term identity here. And so what this algebraic identity says is that if on one side of the wall I have 2 BPS states, 2 BPS hypermultiplets. Hypermultiplets because they appear here to the power 1, and 1 was the BPS index counting a hypermultiplet. And then suppose I cross a wall where these two guys, their phases become aligned. I look on the other side of the wall, what will I find? Well, what I will find, according to this formula, is just 3 BPS hypermultiplets. So here, if you like, I had 2 charges non-zero, 2 BPS state counts non-zero. And here, I have 1 new particle of charge gamma plus gamma prime. And it appears to the exponent 1, so that corresponds to the index just being 1. So this, well, so it's not a bad exercise to actually work this out. Yeah, let's do that exercise. So what does this formula mean? So it's an identity among these abstract transformations of variables, but concretely, in order to check it, just to see what kind of algebraic thing this is, we can imagine just acting with both sides on, say, the variable x gamma. So on the left-hand side, I start with x gamma. I transform it by this operation k gamma. That doesn't change it, because the inner product of gamma with gamma is just 0. Right? This is an odd pairing. So that just maps it to x gamma again. And then I'm supposed to transform that by k gamma prime. That multiplies it by 1 minus x gamma prime, because the inner product between them is 1. In other words, what I get here is x gamma plus gamma prime. The sign has to do with that tricky sign that I wrote at the beginning, so don't worry too much about the sign. But up to the sign, you should be able to see what happened here. So on the left side, I just get this particular thing. And on the right side, if I do this, now this other sequence of transformations, k gamma prime, that maps it to x gamma plus gamma prime, we just saw. Now I act on that, it looks trouble. If I act on that with this, I get something even more complicated. X gamma plus x2 gamma plus gamma prime plus x gamma plus gamma prime. But then, okay, now I've got to finally act on that by k gamma. And that, luckily, multiplies by the inverse of 1 minus x gamma, because the symplectic product there between gamma prime and gamma is minus 1. And this, luckily, just removes the extra unpleasant term, and so I just get x gamma plus x gamma prime. So all right, so the point of this is just that this identity, this sort of algebraic identity, which I'm writing here, which may look a little mysterious, it actually means something completely concrete. You can check it. You can write a Mathematica program that produces all such, that produces these kinds of identities, and checks them if you have them. Yeah. Yeah.
Excuse me, if I give you some Lagrangian for the 2H theory,
yeah.
how do I?
Okay, so the question is, how do I get from this stuff to computing the spectrum of some actual theory given by a Lagrangian? So what I'm telling you here, of course, is not how to determine the spectrum at a given point. What I'm telling you here is, if you know the spectrum on one side of a wall, how to determine the spectrum on the other side of the wall. So if I'm given a Lagrangian, for example, if I'm given the Lagrangian of the SU2 Seiberg-Witten theory, in order to use this wall-crossing formula, what I would have to do is first, I would have to first be pretty good at doing the semi-classical quantization. In other words, I would determine the spectrum of BPS states at large in the weak coupling region by sort of totally semi-classical computations. I'm not saying that's easy to do, but that's in principle a well-defined thing. Now then, so I don't use this wall-crossing stuff for that. Now then, suppose I want to know the spectrum at strong coupling. That's what I use this wall-crossing formula for. So once I know the spectrum at weak coupling, I can determine the spectrum at strong coupling using this wall-crossing formula. Actually, I'll show you that example in just a second.
So this doesn't depend on the matter constant?
It doesn't, no, that's what's amazing about it, is once you get down to this point, once you know the spectrum at one place, it determines the spectrum everywhere else, and you don't have to know anything about the matter. It's totally independent of that. That's what looks so weird about it, is that it's somehow a totally infrared thing. It only uses the sort of parts of the physics which you can see in the deep infrared. So I'll give a physics derivation of this, which will make it a little clearer why it happens. But I agree with you, it sounds nuts when you first hear it. Yeah?
Just a small technical comment. In defining this loop operator, are you not implicitly making a choice of BPS states versus untimed BPS states? Because if you have a state of charge gamma, you also have one of charge.
Oh, yeah, sure. So that's right. I mean, the theory, of course, has in it more than just those two states. When I draw my little loop, I pick up some states and not others. So
no, but on this circle above a given point.
Yeah.
So you mark those phases corresponding to BPS states, but
oh no, also the antiparticles. No, the antiparticles would also be there. So if you look on the back of that circle, you'll see some more lines. I just drew my path in a way that picks up some of the states and not others. Yeah, no, the picture includes all the states. Yeah.
Is there a simple formula for K inverse?
For K inverse? Oh yeah, K inverse is almost as simple as, I mean, K inverse, just put a minus here. Acting on the, oh no, this is just, this algebra is commutative, so it doesn't matter where I write it. Yeah, this algebra is commutative. What's not commutative is the algebra of these operators. Yeah, great. There was one more question. Yeah.
Sorry, naive question. Does this formula say that everyone which can decay will decay, or there's more to it?
It does not say that everyone that can decay will decay.
There is some difference in.
Well, I mean, you're asking, does it have some non-trivial content?
Yeah, exactly.
Let me show you two more examples of the formula, which I think will make clear whether it does or doesn't have. Well, then we can argue about it some more. But no, I know. No, I mean, here, let me point out that if you look at the thing in the other direction, it looks more non-trivial. So here we started with two particles of charge gamma and gamma prime. And we found that on the other side of the wall, they form exactly one bound state. And that bound state has charge exactly gamma plus gamma prime. So in particular, there's no bound state of charge gamma plus 2 gamma prime. That's a prediction of this formula. But we'll see something more non-trivial in just a sec. But yeah, one more.
Sorry, so the way you presented it was that you had to find a solution to this swapping around 2K operators. And it's you have to find the operator that goes in.
That's right, that's right.
So is there a solution to that way to unique?
That's an algorithmic thing. So the answer is yes, the solution is unique, and you can find it. You can find it on a computer. But what I mean by you can find it is, to be precise, if you want to know any particular omega, you can find it in a finite amount of time. And then there's always an interesting question of to find closed form solutions. Yeah. So let me write two more examples of this thing. Oh yeah, sorry. Go ahead. Yeah.
This is probably related to the previous question, but then what is it which determines which wall you're crossing? How does the formula know which wall you're in some zone?
Oh, no, the formula doesn't know that. So that you have to put in. So I mean, that's right. So you have to first do the job of figuring out where the walls are. And then you have to, then you can apply this formula. So, you know, the walls are determined by, well, let's go back to this example. So like in the pure SU2 theory, for example, we just had, so, you know, we start by knowing the central charge functions because Simon and Witten told us the central charge functions. Knowing the central charge functions, we go and we figure out where are the places where the phases will become aligned. And then, in this case, it's particularly simple because there's only two independent central charges. So at that point, all of them become aligned. In a more complicated situation, you would have many, many walls. And, you know, to apply this KS formula in the most naive way, you have to find every one of the walls and then do this algorithm at every one of the walls. Yeah?
What is the formula a property of? Is it about supersymmetry? What does it apply to?
Well, okay, so the derivation that I'm going to give will make it seem to be a, the derivation I'm going to give is pretty specific to this particular class of theories. So it's going to be a statement about n equals 2 theories on the Coulomb branch. It's not, I mean, this omega is particularly the second helicity supertrace. So this particular formula, I would say, is a particular thing about this particular class of theories. Now, some of the lessons of how we prove the formula might well be more general, but yeah.
So are you saying that these people use this particular setting in proving this formula, or is it much more general? Well,
Kontsevich and Soibelman were not interested in gauge theory at all. The proofs of this formula that exist so far, I think all of those proofs apply strictly in the case of n equals 2 supersymmetry, either gauge theory or some of them also apply in supergravity. So, in fact, the original interest was in supergravity. But it's an n equals 2 thing. It's not like a totally general thing about field theory. It's a thing about n equals 2 supersymmetric field theory. Yeah?
Can you show an example where on the right-hand side you have more terms?
Absolutely.
Gamma 2 prime.
Absolutely, absolutely. So let's show us another example of this thing. Okay, so indeed. Sorry, how long am I? Okay, great. So suppose that the symplectic, suppose I have two particles. It seems like a very minor change. Suppose I have two particles whose symplectic pairing is 2 instead of 1. And I'll carry out this same kind of algebraic exercise, k gamma prime k gamma, and just ask, okay, what do I get? What do I get on the other side? And what I will get now is actually an infinite product. So it looks like this: product n greater than or equal to 1, k n gamma plus n minus 1 gamma prime. There's a second infinite product. Let's see, I guess I should write this like this, actually. It's a product from n equals 1 to infinity. So n is increasing in this product. Here I'm going to write a similar product but going down. So n equals infinity goes down to 1. K n minus 1 gamma plus n gamma prime. And then right in the middle, there's one more guy, k gamma plus gamma prime, which appears to the power minus 2. So this is an identity that was written down by Kontsevich-Soibelman already in their first paper about this subject. So here I got two particles on one side of the wall, and on the other side of the wall they form this enormous pile of bound states. Huge pile of bound states, infinitely many of them, infinitely many hypermultiplets, plus this one funny thing that comes with the power minus 2. Now this identity is exactly what we need for the example that I showed you at the beginning. So this is just what we need for n equals 2 Superyang-Mills with gauge group SU2. So let me just copy it here. So what is the picture? So on the left side, I've got the coupling in this. I've got the strong coupling spectrum. So just a dion and a monopole, nothing else. And on the other side of the wall, what am I supposed to get? Well, I'm supposed to get a bunch of infinite tower of dions. Here's this infinite set of dions. And then I'm supposed to have one other thing, and that one other thing is supposed to be the W boson. And the W boson, remember, is in a vector multiplet, and so it contributes to this index with a power minus 2. And so sure enough, so here's the sort of strong coupling. Here's the spectrum at strong coupling, and here's the spectrum at weak coupling. So in other words, this formula sort of manages to predict that you have just these two particles and that they will produce this enormous pile of bound states, this enormous pattern of bound states.
One second. The first term of this infinite sum is actually k gamma itself.
Yes, that's right.
Which is the monopole, and on the left side we call it dion.
Oh, sorry, I use the word dion generically to include the mono. I mean, yeah. So people usually say the semiclassical spectrum consists of dions, but of course one of them has charge 0, and so you might call that one a monopole. I mean, if you like, I could call these both dions. I mean, both of these are dions, if you like. They just, one of them happens to have electric charge 0 in one particular basis. Yeah. Okay, great. So this is the first thing that sort of convinces you that there's something really going on here. And this, I should say, I think it was first noticed by Denef that this formula is exactly what you need. This is Denef's observation, which kind of got the whole business, which got people wondering, you know, why does this, is this formula really something universal about gauge theories? Yeah. Sure, sure. I mean, you have to know, right? I mean, you have to correctly quantize the electric and magnetic charges of the states. Yeah, that's right. That's right. So I mean, this kind of discrete information. I mean, it doesn't come for free. You have to know something in order to use this thing. But you don't have to know as much as you would think. Okay. So that's two examples. I should say, of course, this one also occurs. So this sort of simple one with inner product 1, this one occurs, for instance, in the SU2 theory with a flavor. In the SU2 theory with a flavor, you can already find some walls where this simple wall crossing occurs. Or in the Argyres-Douglas conformal field theories, you find this kind of wall crossing. Now, up until very recently, when I gave talks about this, I always just showed those two examples. But now, let's be bold and go a little bit further. So let's suppose that we have two particles which actually have symplectic inner product 3. Just suppose that you had that. Then you can ask, what does this Kontsevich-Soibelman formula predict? Well, all right, so it gives you some kind of product. It says that the spectrum on the other side of the wall, you just have to solve this. You just have to find the coefficients which make this an identity. You have to find these coefficients, and you can do it. Actually, in this case, you can do it on a computer, but a closed formula for these coefficients is actually not known. I mean, you can determine them to any order you want, but no one knows a formula, as far as I know. And that's despite some attention from mathematicians. This is not an easy thing. So they're algorithmically determined, but actually hard to compute. One thing that is known is that there's a lot of them that are non-zero. So if you look at these slopes and you ask how many of them support non-zero charges, the charges that are occupied are actually dense. So an enormous number of particles, an enormous number of bound states of just these two things. And moreover, they grow, and they grow exponentially with the charge. So in particular, just to give you some idea of what these things look like, so if I look at the Cn comma n, so just the particles whose charge is a multiple of gamma plus gamma prime. Well, the first one is 3, minus 6, 18, minus 84, 465, and so on. So these are supposed to be the degeneracies of particles in some quantum field theory. And so, I mean, for a while, people who saw this formula always sort of figured, well, okay, that must never happen in actual quantum field theories, right? That looks too crazy to happen. So probably it never happens that you have two particles whose symplectic inner product is 3, because this just looks totally bizarre. But recently it turns out that this actually does happen. So this exponential spectrum seems to really occur. And it occurs in almost the simplest theory where people didn't know the spectrum before. So it occurs already in the pure SU3 theory, in n equals 2 super Young Mills with gauge group SU3. So this, I should say, this hasn't been published. This is work in progress. So in principle, it can, I mean, you know, it can be wrong. And when I first saw this, I sort of assumed that it was wrong. But it's survived now for a while. I think it's actually right. So all right. So this might go some way toward convincing you that, at least it convinces me, that this wall-crossing formula actually has something non-trivial about gauge theories, which is sort of hard to access in other ways. So now I've told you what the formula is. And the next thing that I aim to do is to tell you why the formula is true. That's the thing that's going to involve line operators. But I guess maybe this is a natural place to stop, actually. Yeah, so let's take a break, and then the third thing will be the actual proof. This is a physics explanation of why this formula is true.
Okay, so this is time for the coffee break, but let's take some questions for Andy before that.
Yeah.
Could you just show your microphone? Just press it.
So what's the current status now? I mean, for S23 PO super young mules?
No, this is really there. So I mean, you know, what's the status of a thing that people are pretty sure about, but they haven't quite published it yet? But they're confident enough to give a talk about it. They're confident enough to say it in a talk. That's the status.
So this means large class SU3 with 6 flavor of Guyotto theory. This is not much known.
There's very little known, actually. I mean, I'm going to give you, hopefully at the end, I'm going to give you a sort of geometric recipe, which in principle determines the spectrum for every theory of class S. So every theory, people call them Guyotto theory. So every one of these theories that comes by geometric compactification of 6D theory to 4D, there's a purely geometric recipe which produces the spectrum. But in practice, to actually use the recipe to compute the spectrum, very few theories have been really computed out. I mean, so as I say, even the SU3 theory has a lot of mystery in it. I mean, we just found this happens somewhere, but surprisingly little is known.
Any other question? Yes. Press the red button. Okay.
The algebra of the x variables that we have looks like a symplectic algebra, a symplectic group. So this is one possible automorphism. Are there interesting automorphisms apart from K gamma?
Apart from K gamma? So first of all, it's a true fact that K gamma is actually a symplectimorphism with respect to a natural symplectic structure on this thing. I mean, are there other interesting automorphisms? I mean, I don't know. The only automorphisms that have played a role so far in this story, so I mean, in principle, you have the whole group of symplectimorphisms, but these particular symplectimorphisms so far have played a privileged role, and no others have.
But what is the reason that this? What is the reason that one is introducing this symplectomorphism, the particular symplectomorphism? Why?
Okay, so you're asking what's the meaning of this K gamma? Where did it come from? So that'll be the next talk.
Yes, one question from James.
Can you give sort of some clue as to how you work out that what these, for example, you get formulas where infinite products are required?
How to get these coefficients?
Yeah. Well, how do you even know, for example, that you might need an infinite product?
So yeah, so here's what you do. You set your computer up to work in a sort of truncated version of this algebra. So let me be a little more concrete. Suppose we're in this sort of rank 1 case where we just have electric and magnetic charges. So let me introduce two generators. I'll call them X and Y. That's what I used to call X gamma 1 and X gamma 2. So then what you do is you compute, say, modulo, say, X to the 100 times Y to the 100. You just set this equal to 0. If you do that, only finitely many of those terms actually contribute to the resulting formula. And then you get a finite system of equations which you can solve to determine the coefficients of those terms. Having done that, then you replace this by 101 and do it again, and so on. So that allows you to solve this thing kind of iteratively. And if it's infinite product, that's fine. It's infinite. You just see more and more terms as you go on.
Yes,
Is there some physics, conclusion that you can make out of the exponential growth of this degeneracy?
I find it, that's a topic that we're sort of actively discussing at the moment. Right now, our sort of favorite interpretation is that, these states, I mean, naively, if I understand right, naively this would contradict some sort of, thermodynamic arguments about having a conformal fixed point. As you look at the density of states in conformal field theory, it sort of shouldn't grow this fast. So the way we understand it, though, those arguments really apply to the Hilbert space in finite volume. And so what we would like to say is that these states, so there are these BPS one particle states, but that's in the infinite volume Hilbert space, the one particle Hilbert space. So the idea is that those states are kind of getting bigger and bigger, so that this exponential degeneracy would have been cut off if you put the thing in finite volume. But if you put it in infinite volume, there's just these enormous size states of very high charge. I know it sounds weird, but yeah, that's our best guess about what this means.